Yeah, so Marissa asked me to give a presentation today on some ongoing work. It's sort of unrelated to at least current CIRP funded efforts, but of course CIRP invests pretty heavily in morphology models, including with seashore, which I'll talk about today. Um, so as you can tell by the title of my presentation, I'm going to talk about both backwards hindcasting and prediction of coastal morphology change in the Arctic, and also introducing some concepts to do this in a forecasting mode as well. So I'm Nick Cohen. I'm a research oceanographer in CHL, although currently I'm on a 2-year detail to Defense Research and Development Canada and National Research Council Canada. So I actually sit in Ottawa temporarily for the next 6 more months supporting the government of Canada. So perhaps a little bit different than lots of CIRP discussions focused all around the continental U.S., but not surprisingly, you probably know from headlines that coastal erosion is a big problem across the Arctic Ocean. There's lots of reason for this, but as you can see in the upper left-hand side, for the most part, pretty much everywhere along the Arctic Ocean, whether we're in the U.S., whether we're in Canada, the Russian coast, is showing up as yellows, oranges, and reds. So other than around river systems and deltas, pretty much everything is retreating. This is because of the combination of increasing waves, reduction in sea ice, and changing thermal properties as well. And you can see some examples on the bottom panels here in terms of what the landscape looks like at different parts of the Arctic, and you can see that it has signatures of pretty heavy erosion. Some of these systems looks actually a lot like some beach systems in the continental U.S., and others look really different depending on the combination of what the geology looks like, sediment type looks like, and of course the environmental parameters and geotechnical properties. And not surprisingly, in places where population centers exist, this erosion causes pretty big problems. You have infrastructure falling into the coast, runways falling into the ocean, and as a result, we put a lot of effort into mitigating some of this erosional response. So you can see some makeshift erosion in some of the panels with sandbags along the Barrow coastline, where the Alaska District has a big construction project now to reduce a lot of this risk infrastructure. And then in many other parts of the coast, they're implementing either makeshift measures or trying to put in hard features where they can find monetary resources to do this. But it's pretty expensive to construct things in the Arctic just due to logistical problems. So increasingly, we're starting to think about what we can do to reduce risk in the absence of hard rock structures. So the focus of my talk today is going to be first trying to address where, when, and why erosion is occurring, and then talking about what will happen in the future. And of course, we need tools to be able to do that. And lastly, trying to start commenting on how we can use these tools to address suitable mitigation efforts and interventions. So the where, when, and why, we're going to focus on a couple different sites today, trying to pull in local knowledge, field data, and remote sensing. I'm going to talk about a couple sites sporadically across Alaska and Canada, where we've been doing field data collection and numerical modeling across a couple different efforts, both on the civil works and military side. And then to start with, I'm going to introduce one of the sites that I won't focus on heavily on, but I think I had a nice video from there that I think, starts addressing the scale of some of the erosional problems here. For my work in Canada now, we're working at a number of NORAD sites along the Canadian Arctic. One of them is this Pin Main Station, also named Cape Perry, which is in the Northwest Territories of Canada. And well, interestingly, there's an old village here, and so even though it's largely a military site, there's lots of historic artifacts. The population center has moved a couple decades ago, but now, as you can see in the bottom right-hand panel, the graveyard where they buried a lot of the community members, people that actually worked at the former the NORAD North Warning System site, is within about 10 meters of this bay system. And so I'm just going to play a video from the summer. We had put out a bunch of hydro instruments. We collected bathy and topo and did lots of measurements trying to understand what the baseline conditions were for this site, in part so that we can project out how long they have till this graveyard falls into the water, working with the community to start coming up with mitigation solutions to this. So it should just be a couple more seconds, but you can see that even though this is a really microtidal site, on paper, the tides are only something like 20 centimeters. There's a lot of variability in the water level. It's driven really by regional wind forcings. And you can see there was an event that came in later in onset of ice where you saw a loss of something like 2 meters of this bluff system. And notably, the biggest erosion occurs when thermal processes don't play a big role, which is really late in the fall before the onset of ice. But it's also when we have the most stormy conditions. So anyways, I'll just let it play one more time. That it doesn't really take much in terms of water levels and waves to start eroding a pretty significant amount of this landscape. So next, we're going to switch gears and talk about or focus on what we how to plan for this erosion, what to do to mitigate the risk. Not surprisingly, we're going to focus on models for that. And I just came up with a sort of rough outline of two types of models we might want to do depending on use for different types of purposes. For a planning model, we might be focused on longer term applications, perhaps multi-decadals. We can plan out what the risk profile is for a certain site, whether that's NORAD site or one of these community locations. And because we're the Corps of Engineers, we care a lot about engineering models in terms of the what to do. So I'm going to talk about two general modeling approaches today. First, I'll actually talk about a modification of the dune response tool. This was a lightweight analytical model that was developed under a CIRP program, but we've since modified it to account for Arctic relevant processes. So it's really fast, lightweight. We can get multi-decadal answers within a matter of seconds or maybe minutes. And then secondarily, I think people on this call are more familiar with seashore and actually adapting that to include Arctic relevant processes as well, where we can ask more engineering relevant questions. So I'm going to switch gears and move from the Canadian coast over to the Alaska coast, because we done a bunch of work modifying this dune response tool to Arctic settings at Point Hope, and so I'm going to talk a little bit about that. I don't think I presented this before at a CIRP TD, so hopefully this is relevant. In previous work under Engineering with Nature project, and then we have a current ESTCP project. ESTCP is a military R&D program. We have ongoing work at Point Hope. As you can see here, the north portion of this coastline is pretty heavily erosional, so deep red colors indicating that there's significant land loss. So this actually triggered the community to relocate something like 30 or 40 years ago. They actually moved inland a couple kilometers. You can see on the upper left-hand side, the community is relatively far from the coast now, although there's pretty significant cultural artifacts still located by the coast. And also, well, they did have a runway that impinged on the coast, although they just realigned the runway in the past 2 years to so that it was no longer falling in the ocean as well. One of the reasons we started doing work here is because there's a reasonable amount of airborne LiDAR data and environmental data, quite good bathymetry data actually, and in many Arctic locations we're really limited by data availability. So as we want to start adapting tools and understanding whether they work well, of course we want to focus on an area where we have the data to inform that type of validation. So as we started doing work in Point Hope, we're really focused first on this planning level type model where we wanted to think about long-term risks. So the community was really interested in terms of protecting ice cellars along the coast so that they obviously can't move inland. So these are features that were embedded into the sod along the coast where they currently store whale meat after their hunting season. Not easy to move, and they really don't have the geologic properties elsewhere to build new ice cellars. So really focused on multi-decadal scales. And so as we look at the tools we have available from more temperate sandy systems, there's some examples of a range of complexity of typical nearshore morphodynamic models on the right-hand side here. For this multi-decadal scale, we focused on an empirical approach using starting to modify approach from Promston and Holman, which is focused on dune erosion, and starting to modify that for the Arctic coast. So I'm just going to walk through generally what this lightweight tool does, but we'll try to get to the fun shortly, which is trying to think about long-term projections of future land loss along the Arctic coast. So in a simplistic sense, we're focused on a 1D cross-shore profile here. We have ocean on the left-hand side, tundra on the right-hand side, and beach system in the middle. We care a lot about what the water level does. As I said before, these are generally microtidal systems, and so tides do exist, but they're pretty small. More than anything, we have to care a lot about the fluctuations from storm surge and other non-tidal residuals. And depending on what part of coast you are in the Arctic, sea level rise might be pretty significant as well, although it's quite spatially variable depending on the uplift rates. And not surprisingly, if we're on the outer coast, as we are in Point Hope, then we care a lot about wave-driven forces as well. And these can be quite significant during storms in terms of contributions to both beach evolution, but also wave run-up and subsequent response on tundra. So if we care about wave run-up in a simplistic framework, we can characterize this with a number of different empirical models. Here we have the Stockton 2006 wave run-up equation, which is quite widely used, and we're going to use this in terms of our analytical tool here. Ultimately, what we found from laboratory studies and in the literature is that by and large, volume losses of backshore systems, things like dunes, but also tundra, are related to the amount of freeboard of the wave run-up above the dune toe, or in this case, the tundra toe. And so there's an equation here that aims to characterize the estimated volume losses of material from a backshore cliff based on wave impact theory. And lastly, if we care about multi-decadal scale, we don't just care about waves and things like sea level rise. We also care about how the shoreline is evolving as well. And so this is parameterized in this simple model because ultimately what the beach does has a pretty big impact in terms of wave run-up dynamics and the likelihood of collision of water with the tundra. So I'm just going to show a video of this profile model over, I think this is a 14-year timescale using measured still water levels from a nearby tide gauge and modeled wave heights and wave periods from offshore. This is from ERA 5 in this case. But we did put out a wave buoy at this site to validate that ERA 5 was doing a good job. And you can see in this simplistic model where I just talked about the 4 some odd equations that go into the code, we can predict landscape response. So how well does this do if we do this in a hindcasting mode? Here we have at 9 different profiles along the coast. We have LiDAR data in gray from 2004. We have another airborne LiDAR survey from 2018 shown in blue, and then the model out of the box with no model tuning, still using coefficients suitable for sandy dune systems is shown in the cyan line. And you can see by and large, the model actually does a pretty good job of recreating the expected backshore response without any calibration. So that gives us some optimism that at least porting some of our morphological tools from continental U.S. systems or other more temperate environments works okay in the Arctic. And I'll explain shortly why that might be in this site. I realized that colors didn't show up here, but we have 2 timescales here comparing the model performance on the x-axis to the field results on the y-axis. But generally what you see here is across both multi-decadal scale and annual scale, where we had another airborne LiDAR scan in 2019, that the model does a pretty good job of recreating both the magnitudes of response at different points along the coast. So if we do a good job of of recreating the past, then of course we want to start thinking about the future. The problem is that we don't have necessarily a good handle in terms of the potential for extremes in the Arctic, in part because our observational record is pretty short there. And we know from recent events like Murbach and Halong that perhaps we haven't seen a lot of the extremes. So, um, and perhaps these extremes are now being exacerbated because there's lots of changes in the Arctic, right? Air temperature is increasing. We have a reduction in sea ice extent, and there's lots of implications in terms of what the landscape might do because of this. Among them is that waves are generally getting bigger. So as we reduce ice, which you can see schematized here on the left-hand side. Okay. Well, I apologize for that, but yeah, government internet connections are always spotty. So, well, now that we have successfully hindcasted results, and we know that there's potential for pretty significant future changes in terms of what the oceanographic and meteorological climatology looks like in the Arctic. We need to think about how to embed that into a numerical framework so we can suitably characterize risk in the future along the Arctic coast. I'm not going to dive too much into the details, in part because Dylan Anderson gave a CIRP technical discussion a couple of weeks ago talking about this oceanographic emulation framework, which I'll reference this paper here and talk about a couple of the details. But generally, what we've been doing is taking approaches to statistically emulate wave and water level conditions along the coast. That's been pretty heavily validated and utilized along the Atlantic and Pacific coast, and we've ported this now to the Arctic as well. Things that we have to do differently here is characterize this sea ice component, because as I was starting to talk about before I got cut off, sea ice is quite relevant for a number of reasons, but among them is the generation of wind waves. Of course, when we have large open water conditions coincident with storms, we can generate large waves. But the second that there's ice on the surface, even partial sea ice, then we reduce this the wave generation pretty significantly, and this is a key driver in terms of erosion along beach and tundra systems. So the first thing that we ultimately had to do was generate an approach to deal with sea ice stochastically in this framework. In this emulation framework that Dylan talked about a couple of weeks ago, ultimately the key driver of waves and storm surge and other water level signatures is from weather. So this approach characterizes weather regionally and comes ultimately up with sequences of weather patterns and linkages with joint dependencies between waves, winds, water levels, and other parameters. In a fairly clever way, what we can ultimately do with this framework is come up with downscaled coastal conditions. So here's just an example of really any parameter. In this case, let's say it's wave height, that we can come up with a time series of continuous water level conditions. And in this case, there's gaps because this would be during the iced over conditions where we wouldn't have any wind wave generation. And if we're able to come up with downscaled coastal conditions, let's say hourly conditions, we can really feed any types of hazard model. And we can do this to feed, let's say, a tundra evolution model like I just talked about. One of the nice things is that in a statistical framework that's quite computationally efficient, we can let's say roll the dice numerous times. We can come up with different plausible sequences of waves, water levels, and really any other conditions to feed these models to come up with numerous estimates of landscape response. And in this way, we can come up with probabilistic estimates of response, which is enables us to come up with some risk-based forecasting products. In this case, I've mostly talked about this modified dune response tool. Let's call it the Tundra response tool, but we can also do this with Seashore as well, and I'll talk about that momentarily. So since we're going to talk largely about looking into the future, and I've skipped most of the details of what this framework looks like, let's just make sure that first it does things that are plausible for the Arctic. So here you can just see time series looking out 25 years. Upper panel is looking at still water level. So as I talked about, even though we're in a microtidal system, we can see really big fluctuations in the still water level, which is what we expect along this area, really driven by regional wind patterns. As we look further down at the significant wave height and peak wave period panels, what we start seeing is that there's variability over time in terms of what the ice-free season looks like. So those little gaps between periods where we have numbers for the wave heights start getting smaller and smaller as we have more open water conditions, and we have the potential to grow more storms when we have water conditions and no offshore or landfast ice. What we see when we're able to do multiple iterations of this stochastic framework is that we get different time periods depending on when we run the model for when we might get extremes, and the combination of extreme wave height events and still water level events is quite relevant for the potential hazards for both morphological response but also for flooding. So a couple other things just to confirm that this model is doing okay. On the upper left-hand side, we can see an example of the hindcast from ERA 5 waves. As I said, we used in our hindcast before. It's also used as an input condition to this oceanographic emulation framework. And what we see is that between early summer in June up through November before the ice hits, that generally we see a slow increase in terms of both the average and higher percentiles in terms of wave heights. And we're able to recreate this in this oceanographic emulation framework on the upper right hand side as well. So we're able to replicate a lot of the the return periods with confidence that we've seen from the historical record before we do any forecasting. Other things that the model is able to recreate when we start including changes in air temperature and start including changes in the open water conditions that have feedbacks and waves is that we start seeing a shift over time into the future, shown by the colors on the bottom panels here in terms of what the wave heights will do. So what we start seeing in the future is that we get increasing wave height conditions, particularly early in the season. And we start seeing shifts in the wave direction as well, which might have important implications in terms of littoral drift. So now that we at least see generally that this framework is recreating a lot of the expected response in terms of future waves and water levels, we can't validate all the behaviors, but we can we can spot check that it looks right conceptually. We can feed this into a morphological model. So if we feed this into the same morphology model that I showed before at Point Hope, we can look at a time series out 25 years into the future. And here it's just showing the horizontal retreat of the tundra. So what we see is over the next 25 years, we might expect that the landscape to retreat by, let's say, 33 meters, but it's heavily driven by extreme storm events that we see episodically, 5+ meters of retreat a couple different times. Of course, we can run this same framework many times because both this oceanographic emulation framework is very efficient, but the morphological tool is also very efficient too. In this case, less than a couple minutes. And what we start seeing is that this different combinations of wave and water level sequences, we start getting different morphological responses, which is not unsurprising. And if we do this 100 times, or let's say 500 times, we start building up, a suite of potential responses. And that envelope of variability might be pretty significant. So we see a pretty clear lower bounds of what we might expect in terms of retreat, but extreme storm events might double the expected response. So we look at probability distribution of these retreats from those suite of 500 cases. What we start seeing is that indeed the extreme storm event combinations might lead to double of what the mean expected response is, both in terms of volume loss and in terms of horizontal retreat. So as we start thinking about design criteria and what we're trying to build and withstand for this might be important in terms of thinking about what we're trying to protect. If we map these changes on a map, it's a little blurry, but the background here is you can see the white areas are actually showing where these ice cellars are located. Um, what we start seeing is that by 2050, a number of these ice cellars are lost no matter what. And I think the majority of them are gone by 2050 if the worst case result happens. So once again, starting to use this information to think about what the potential risk might be in the future in the no action case. Notably, in these simulations, we didn't actually include thermal processes. As I said, we just used the parameters for sandy beach systems out of the box, and the model did pretty well. There's a couple of reasons for this. One is that this is a pretty low-lying cuspate foreland system, so it's mostly like sands and gravels. There's actually not a lot of permafrost here, so it probably represents sandy system. Secondarily, the biggest response mostly happens from storms in the late fall. So this is when the active layer thickness would be the deepest. So part of it is because of the geologic characteristics of the site itself, is that it's mostly composed of fairly mobile sediments, which is atypical relative to some other Arctic landscape coasts. But what we did do is in this model include a term to be able to characterize the active layer thickness. This is basically the depth where you have mobile sediments before you have a completely frozen layer. So this is mostly a sort of a thought experiment because we didn't have a lot of validation data for this particular site. But if we included relatively small active layer thickness. So this is parameterized here by air temperature time series. So we continuously recalculate the active layer thickness based on the dynamics of the site, but there's basically a maximum active layer thickness that you can get based on the soil properties. What we start seeing is that in the model framework that no matter what, we're going to continue to have pretty significant erosion of the coast. But the envelope of variability gets considerably constrained because it's controlled more or less by the thermal dynamics. But as soon as you have erodible material, generally it starts getting eroded from waves. Other things we can start doing in this model framework, in part because we're able to do this really efficiently, is think about the relative roles of things like sea level changes and shoreline changes. And so what we see here is that if we have a small amount of sea level rise, that we start increasing our erosion modestly of the tundra system as you have more collision. But at some point that there's a tipping point where we have really accelerated erosion, which is more or less what we would expect. And secondarily, we can change the shoreline change rate in the model. And not surprisingly, as you retreat your beach system more, the tundra also retreats significantly more as well. So there's a close coupling between the beach and what the tundra does, at least in the model framework. So I wanted to introduce this tundra response tool, in part because I wasn't sure that people in CIRP had seen it before. Things that it can do is tell us, well, we can hindcast the past, and we can also start looking to the future. But one challenge with an analytical, pretty simple model is it's a little hard to start mitigating for the risk. There's some things we could change, let's say about adding maybe a beach nourishment or changing thermal properties of the soil. But we're not able to actively add in like interventions like breakwaters or dynamic revetments or complicated structures into a model like this. So that moves us over to things that we've started adding into Seashore to really get at more of these solution type questions. So currently, as I said before, I'm currently based in Ottawa, Canada, supporting the government of Canada through the Deputy Assistant Secretary of the Hermes Office, SEDEC. So they've funded basically a 2-year detail to support adding in capabilities into Seashore and expanding our Arctic coastal hazards work for the Army in the North. And we're closely with Defense Research Development Canada and other groups as part of this. One of the sites that we're working at significantly is Arctic in the Northwest Territories. You can see a picture of this in the bottom left-hand side, and then some time-lapse shoreline evolution in the right-hand video. What you can see is that it's pretty active landscape change, particularly at this Tuck Island site, which you can see in the sort of upper right-hand side. There's not a lot of infrastructure on Tuck Island itself, but it's a barrier for much of the community, preventing waves from reaching a lot of the built-up areas of the town. Notably, you can see on the picture on the left-hand side, there's also a big radar station. So this is also a relatively important defense asset, both for the Canadian military, but also for the U.S. as well, because all of these NORAD, North Warning System sites are actually majority paid for by the U.S. government. So if we focus in on this Tuck Island site that I mentioned before, we're lucky that there's quite a bit of data, topographic data at least. So looking at this slice on the bottom right-hand side, you can see that between 2004 and 2025, that there's been pretty steady retreat of this whole landform. There's not a lot of bathymetry data for the area. There's some community bathymetry data from like the 2024, 2025 timeframe. So you can see it's really shallow offshore this area, but we don't have a lot of repeat bathy data, and that might be important in a minute. You can also see a little blip in 2025, and this is because they actually built a rock revetment in the past year there. So I actually saw the construction last winter. I went up and saw them building it on this barrier island system. But one of the key reasons that we're working the site is that there is a lot of data here, and that helps, considerably with model testing and validation and improvement. So before we stuck with a lighter weight empirical model, but in this time we're gonna focus on seashore in part so we can ask more of these questions about, well, what do we do about this evolving risk in the Arctic? Because as we know, we need to protect infrastructure, we need to protect people, and so designing solutions becomes important. I think probably many people on this call are familiar with Seashore, but of course it's an open source model that's pretty widely used within the Corps of Engineers. I imagine Brad's on the line, so Brad Johnson is one of the key developers for this. It has lots of advantages that, it's not as fast as the analytical model I talked about before, but it is really quick generally. So we can simulate, let's say, a year of profile change in a couple of minutes, and reasonably well validated along many coastlines. Like all morphological models, it has lots of assumptions and lots of limitations, but that's just the field of coastal sediment transport in general. So the first thing we're going to do is run Seashore out of the box for this time period where we do have data. And if we do run Seashore in this case without any thermal controls whatsoever, what we start seeing is that the model overpredicts the amount of erosion. This probably isn't too surprising for anybody here, that let's say we overpredicted the erosion by 50%. So out of the box, our morphological tools, don't do a perfect job in terms of recreating the past. But things that we can do to start improving this is similar to this other model. We can add in representative thermal dynamics. In this case, we're going to add in an approach for dealing with the active layer thickness. And secondarily, we're going to also add a hill slope diffusion model to the mix to deal with non-driven or non-wave driven responses, because what we see oftentimes is that there's thermally driven controls in terms of landscape response, particularly at the tops of hill slopes. So if we add these thermal capabilities into the model, I'm just showing another hindcast over this 20-year time period, we start seeing that the model does a pretty good job of recreating the bluff retreat. So I'll just note a couple things. Now, at least in this one case, when we have good offshore wave conditions and water level conditions, that it gets the bluff retreat pretty well. Conceptually, it's probably not doing a good job of simulating where that sediment is going. There's lots of reasons for this. We don't have a lot of bathymetry data here to back this up, but generally these tundra bluffs are composed of a lot of really fine-grained sediment in addition to some sands. And so in this case, probably a lot of that sediment is actually transported far offshore, but in this case, it's deposited in the near shore. So mostly a limitation of just how we're treating sediment in the model. And it's also able to deal with some of the hill slope dynamics in the back of the island is that we also see that really isn't wave driven. Next, what we're going to do is since we have some confidence that Seashore is doing okay in terms of hindcasting the past year, with a lot more validation needed, is we can take the same approach that we did before with Point Hope, but now we can project out into the future what that response might look like. So we're going to do this now with a 20-year time horizon with Seashore, using emulated oceanographic conditions from Dylan Anderson's framework. So if we project out into the future 20 years for one time series, one potential iteration of future wave height and water level conditions, we get about a 20-meter response of the landscape. So you can see a simulation here of that expected retreat over 20 years. So we're going to zoom into this area, and if we actually run, I forget how many cases this was, 20 or 50 or 100, all of these orange lines are showing potential future responses depending on stochasticity of the future environmental conditions. And the yellow line here is just showing the mean of all of those potential profiles. So if we come up with a probability distribution of future retreats, it could be anywhere from, 8 meters to let's say 38 meters. So a wide potential response just based on stochasticity of the wave heights, of water levels, and the air temperature changes in the future. Although generally everything is saying that this landscape is going to continue to erode. Last thing, I'm going to just show one more example with this model to bring it back to Alaska. It was a little bit more relevant for the Army Corps of Engineers. We do have a ESTCP project here that's collaborative with colleagues Krell, so Lauren Boucher and Tom Douglas are at the Fairbanks, Alaska office, and then we've been working with West Point and the U.S. Naval Academy on a project here. So this site morphologically is similar to many of the other sites we've seen, pretty rapidly eroding landscape. Here, there's some evidence of quite a bit of thermal decay if you look at some of the pictures on the right-hand side. And the site here, the community is not located on the outer coast. It actually has a barrier island in front. So here we've had to adapt the tool also to start dealing with, more estuarine shorelines where the offshore wave don't matter, but we need to calculate local wind wave generation within this lagoon system. But if we modify this oceanographic emulation framework to use wind forcings to project out the waves in the lagoon system, and we characterize the future expected still water level changes, we can also come up with projections along the estuarine coast here in terms of the response. So showing the purples to yellows is a 25-year prediction along the Point Lay shoreline in terms of the expected erosion. And just the right-hand side is just showing some contour evolution changes, showing that we have changes both at the upper part of the profile, really thermally driven, and then wave-driven export of these tundra bluffs, more from wave and water level forces. We can do this probabilistically as well. So it's just showing an example, I forget, of maybe 30 or 50 simulations, in this case projecting out into the future of the expected response. And what I'll say here is that interestingly, along this coast, the ensemble is pretty narrow. We only see an expected variability in, let's say, 5 meters of retreat, in part because this is much more thermally driven here than it is wave driven. So the extremes matter a lot less. It's mostly controlled by the thermal dynamics along this estuarine coast. But the map on the right-hand side is showing the projections of the seashore results along the, on this time horizon, we start directly impinging on infrastructure. So ways that these tools can start being used to, inform risks to Arctic communities. So, well, I think before this talk, you probably already knew that coastal risk issue along Arctic coasts. I've talked a little bit about the tools starting to be used for predicting how that erosion might evolve with time, but it's really this big question about how we mitigate risk that's driven a lot of these questions. So there's lots of things that are currently working on adding into seashore. I just wanted to give one example of this modified framework, starting to include some of these combined thermal processes and morphological processes. But ongoing, we're adding in lots of soft infrastructure solutions, trying to add in things like dynamic revetments and trying to start dealing with things like woody debris and other materials that are more prevalent in the Arctic. This is just one simulation showing, let's say, conceptually a breakwater offshore to dissipate wave energy. And you'll see three different lines. One will be the breakwater in blue. The case in yellow will be if we have no thermal processes included whatsoever, and the red line will be the baseline case with waves and water levels, but we include thermal processes in this coupled model that partially will slow down the erosion. So hopefully this video is showing, just showing on the left-hand side the profile evolution. I realize I cut off some of the bluff here with where the legend is, and then just the volume changes, the volume losses of that bluff system for these three different cases, where you can see that within this coupled seashore model that by starting to include the thermal processes that we are predicting considerably less erosion over time. Let's say in this case it's by something like 20%. Additionally here, if you include a breakwater in the mix in this framework, then we're also considerably reducing erosion. So starting to use this model for both conventional and natural infrastructure to come up with potential solutions in the far north. Oh, I think I just made it back. Do you hear me again?
Yeah, I hear you now.
Okay. Well, at least it was on the conclusion slide, so you've seen everything at this point. But yeah, just in closing, I think we've started developing lots of tools that are useful, just or have lots of promise for predicting both past and future erosion. Of course, we always need more data and validation, and that's pretty hard to come by in the Arctic. But that's part of why we do research, right? To expand our understanding of how well these tools work, both out of the box and for future applications. So with that, I'll take any questions if people have them before my internet cuts out again.